Thanks a lot for coming along. So yeah, we're going to be talking about macOS kernel fuzzing and our attempts over the last sort of year, 18 months of this project. So quick agenda. I'm going to go through our system call fuzzer, OSX fuzz, which we recently open sourced the framework for. We're going to talk about how we approach scaling up our fuzzing efforts, our code coverage as well, and how we've started looking at implementing code coverage into the fuzzer. And then Alex is going to talk about IOKit and mesh fuzzing and Opal robot. And then talk about some comparisons between the two different fuzzers, and then just some conclusions and brief chat about some of the bugs we found towards the end. So OSX fuzz. This came around because last year we presented at DEF CON on our Windows kernel fuzzer. You know, kernel fuzzers, why do we want them? Well, we're looking to try and find sandbox escapes, you know, getting root, etc., etc. And we found that our Windows kernel fuzzer was pretty effective at finding bugs. You know, we found tens across a 24-hour fuzzing run, which is reasonably effective. And we also found it scaled pretty well as well. So our fuzzing efforts were concentrated on Windows 7 and Windows 10, and it worked pretty well. So we wanted to see if we could basically just use the same principle, but target macOS. So we tried to design the fuzzer to be sort of agnostic to the OS. That turned out to not quite be the case. So this talk concentrates more on what we did for macOS. So just to go through some basic principles of the kernel fuzzer, we have sort of a bunch of functions in it that basically return fuzzed values. We quickly found actually though that you don't really want to have random values in there. So initially we just sort of, you know, just load of rubbish in there basically to try and find bugs, but actually most calls don't work because the arguments don't make sense. So instead what we did is we changed this to be a predefined list of good values per data type, which increases the likelihood of a call, particularly things like syscalls or whatever, actually succeeding. And if a call's succeeding, then that's more chance of us actually finding bugs. If a call just fails out really early on, we're never going to find bugs. So when doing kernel fuzzing, it's quite important to make sure you're actually providing reasonably valid data. Otherwise, it's just not going to work. Another big aspect of the fuzzer is what we call an object database. And what this does is it allows us to store very specific objects, such as file descriptors that a lot of the calls are expecting. So you can't just, you know, if a call is expecting a file descriptor, you can't just give it a random int and expect it to work. It's actually expecting to receive a valid file descriptor. So what we do is we store these in what we call an object database. And all we do is we just create a bunch of valid objects at the launch of the fuzzer. And as the fuzzer's running, it might start returning to us things like more valid file descriptors or, you know, whatever else. So we can just pop those back into the object database. One of the improvements since we last looked at our Windows kernel fuzzer that we've implemented is the ability to ask for an object of a specific type. So as you can see on the slide, what we're doing here is we're sort of getting a random object by its name. So IO surface ref, so that call will return to us a valid IO surface ref that we can then pop into a syscall or an API call or whatever, and launch it, and hopefully the call will succeed. And the second one's just doing an IO connectee, so just giving us an IO connectee back. As I say, we generate a bunch of these objects at fuzzer launch. So the first one there is just going through and generating us a whole bunch of valid file descriptors. You'll see from the code that we've actually taken this from our, pretty much ad-lib from our Windows kernel fuzzer, so you'll see loads of references in there to handles, obviously not a thing on macOS, but yeah, just lazy coding from from us basically. The other one there is going through and trying to generate us a load of valid IO connectees as well, which will get pushed back into the object database. So if you haven't seen the code up on GitHub, if you ask our fuzzer for an object, what you actually return back to you as an object struct. In there, what you have is the value, so that will be the value that you're to use in your syscall or API call. You'll then get the index, and this is an offset into the database. So the database is actually deterministic, so it'll always get created in the same way on each fuzzing run if we use the same seed. So what we can do is, during a repro run, we can just look into the database at the offset and grab the same value. The reason we need to do this is obviously we can't just, if we get an int returned to us for a file descriptor, that will be different on each run, including on repro runs. So we do this to make sure we get the same type or objects returned during a repro run without relying on the real value. And the last thing you get is a tag, and this is just so we can check to actually make sure we got returned the correct object type. Again, it's quite important on repro runs, because otherwise we'll just get different things happening on a repro run. So syscall fuzzing. All we did for this was just pull out all the BSD syscalls, which Apple helpfully open source from the syscalls.master. And we also implement maze traps as a separate syscall table. Initially, all we did was auto-create just a big array of syscalls and then automatically try and convert these to known types that our fuzzer would be able to sort of use, essentially. So, things like ints, bools, chars, all that sort of stuff. If we didn't know what something was, we'd just basically give it a void star. So, if it was just a struct that we hadn't implemented or something else like that, we'll just say, right, well, there you go, have a void star, and hopefully something will happen. So before, what we would do is just have a big load of assembly that would take all our arguments, set up the syscall, and then call it. But actually on BSD and Mac, there's a really nice syscall function, which works pretty well and worked pretty well for us as our fuzzing, so all you do is you give it the syscall, the arguments you want to give to the syscall, it'll go away and execute it for you, and just return to you the syscall return value. Really simple, really easy. So if you're going to do syscall fuzzing, recommend using this. So just at a really high level, really simple, all the fuzzer does is it goes away, picks a random syscall from a massive array that we've auto-generated, generates the arguments based on that, and then just call the syscall. So this approach worked okay for really basic syscalls. If the syscall was expecting an int, for example, yeah, it would probably work. But the vast majority aren't just expecting an int, they're expecting something a bit more complicated or a struct or something like that, so they just didn't execute because the arguments didn't make sense. There's some reasonable checking going on to make sure that the arguments make sense. And we just weren't putting in the effort, basically, to do that originally. So essentially, it was time to stop being lazy and try and write out each syscall individually. That may not sound like a tough task, but there are something like 550 syscalls for BSD. Then you've got all the maze traps and all the API calls on top of that. So there's a reasonable amount of effort went into writing all these. So now what we have is that each syscall is now a function itself. It's essentially the same principle as before, but what we try and do is make sure that the arguments we're going to provide to the syscall are correct. So, if it's expecting a struct, we'll go away, create that struct, and make sure the arguments, look reasonable. And this worked pretty effectively. The vast majority of syscalls now execute, and we're actually doing something. And it was shown that before we didn't get any bugs, now we do get bugs. So it seemed like a pretty reasonable approach. With any fuzzer, it's quite important that we log what we're doing, because we need to be able to repro, especially when we scale up and stuff. The approach we took, which is probably not the approach we would do again, is we log valid C. The idea behind this was we wanted just a test case out that we could compile and it would cause the same crash, which I guess makes sense, but creating those login statements up front is very difficult. And then you spend a lot of time trying to debug login statements when you're trying to do a repro, because whoever writes valid C on the right first go, right? The way we do it is the fuzzer will send what it's about to execute over a network port to fuzzer control, and then we just wait for a response back to make sure that fuzzer control got our log file, which sort of helps us avoid having non-reproducible test cases. So that is a little bit slower. Initially we were just logging to disk, but what we were having was some caching problems, so we'd get a crash, but we'd be missing the last few lines of our log file, which is obviously not helpful for repros. The other thing we do is we take a log of the seed value, so it's all written in C, and we just use ran full decisions. So all we can do is just replay the fuzz out exactly as it was by giving the ran the same seed number, and it will just go away and execute exactly the same as well. So if we do have problems with log files or whatever, we can still get the same crashing test case out. So this is what essentially a syscall in a fuzzer now looks like. So this is the exit syscall. Probably not much point fuzzing this. So the first thing we do here is we generate what we call a variable ID. So obviously we have this massive C statement that's going to be our log file. So we need to make sure that all our variables that go into this log file have unique names, otherwise it will never compile. Then what we're doing is we're getting our integer, so just a rand int there. We're logging what that integer is. And then what we do is we log the syscall, and it's actually important to make sure we're logging the syscall before we execute it, because otherwise if we get a crash in the syscall, we'll never know what it was that executed. We then execute our syscall, and then what we do is we also log the return value. And this is actually really helpful because it means we can quickly just skim through our log files and see if there's any syscalls, you know, if the same syscall's failing over and over again, we can go away and just fix that up to make sure it works properly. So the other thing we have in the fuzzer is we've implemented a whole bunch of what we call library calls, but these are just a catalog essentially of common API calls. Again, it's a very similar approach to the syscall fuzzing, and we've implemented API calls for IO service, hypervisor, IO-id library, and IO-kit. So again, this is an example where it's using the object database to get an IO service T object out before calling IO connect add ref. So this is what sort of our new fuzzer loop looks like after the first iteration. So we either go away and choose a library call, a syscall, or a maze trap, generate the arguments for it, and then make the call. You know, does it crash? Yes, no. Okay, carry on if it doesn't. And then we'll do that, you know, a few 100,000 times. Being reasonably effective, we found a few bugs with this, which Alex will cover later on. The framework for this we've recently put up on GitHub. So it's up on the MWR Labs GitHub page if you want to have a play or have a look at how we've approached it. So scaling, obviously, with fuzzing, we want to, you know, try and run as much as possible and run at scale. You know, why run one fuzzer when you can run hundreds? Because that's just going to mean we're more likely to get bugs. The other thing we're really keen to do is to auto-capture bugs that we find, getting kernel dumps, basically reverting the VM, doing all the, just automating it as much as possible. So it's literally click and play, launch a fuzzer, it'll go away, launch hundreds of instances, and then hopefully we'll get a bunch of bugs back at the end. So we have a bunch of Python wrapper scripts that just control everything. So initially we were using Fusion, and we just used VM run for most of this. So, you know, prepping VMs, generating snapshots, reverting, pushing new instances of the fuzzer into the guests and everything like that is all done via these Python wrapper scripts. We've recently been exploring QEMU as well. Reason for this is we wanted to be able to investigate using code coverage, which is a bit simpler on QEMU. Obviously, the licensing terms for macOS are very strict, so you must make sure that you run any guests on Mac hardware, and we definitely don't have any AWS instances running this at all. So if you work for Apple, please don't sue us. There were some challenges with this, so some of these we've managed to overcome. So things like NVRAM support, so we use OVMF and Clover for this. Getting kernel crash dumps out, so the IO kernel debug interface was initially a problem, but we're using VirtIO net for that now, which seems to work pretty well. And if you were to run it on something other than Mac, it's quite nice and works pretty well under Linux as well. So we've heard. The last thing that we haven't quite got working properly is memory snapshot support. So what we want to be able to do is just, either at the end of a fuzzing run or after a crash, just revert back to a snapshot, because that's a lot quicker for us. Currently under QEMU, we haven't quite got that working, so we're still investigating that. So it does slow it down a bit under QEMU, but the good thing is we can spin up many, many more instances of QEMU than we could with Fusion, because it's much more lightweight, and we could potentially run it on something that isn't Mac hardware. So that's just a diagram that shows how we run things. So we have a bunch of OS X fuzz instances running on a bunch of macOS guests, which run on top of whatever hypervisor we've chosen, QEMU, Fusion, which sit obviously on top of a macOS host, which is running our logger and panic daemon, which is taking all the kernel crash dumps. And then what we do is we'll have a whole bunch of these hosts running our fuzzers. So we push all these crash dumps into CouchDB. It works pretty well because it means we can do deduplication of crashes across a whole bunch of hosts. So if we've already seen a crash on another host, all we do is we log that we've seen it again, but don't bother keeping any of the kernel dumps or logs or whatever, because we've already got all that. So code coverage. So we've started exploring how to do this, and we've sort of started using NCC's Triforce in order to gain code coverage. At the moment, we've only got a really basic setup. So to do this, what we've done is backport all the QEMU patches from future QEMU releases to support macOS Sierra under Triforce, as well as adding in the sort of Clover support and everything else. We will publish these changes to Triforce at some point once it's a little bit more stable, so others can have a play as well. So this is sort of what our new, run looks like. So we'll choose a call, whether that's a library call or a sys call or whatever, and then we'll start tracing in the kernel. We'll make the call, stop the tracing, because tracing is quite slow, so we don't want to leave it running all the time, and then we take the coverage information. So at the moment, that works, but unfortunately, we're kind of not doing a huge amount with that coverage information. What we want to be able to do is, if we hit new code paths, we want to keep those arguments and possibly use them for future runs of the fuzzer. So, we'll be able to tweak those arguments and start exploring new code paths. If we don't hit new code paths, or we're just constantly hitting the same thing over and over again, that means we can figure out, is the call not working, or is it not worth carrying on with this type of call because we're not getting anything out. It needs a fair bit of work at the moment because our original design really didn't take into account code coverage. The idea was it was just something you could put in a VM, run, and it was all self-contained. Whereas with code coverage, we need to push code coverage out of the VM, do something with it that's useful, and then push that back into the VM. So we just need to think a little bit more about that. But what we'll do is we'll push those changes out to Triforce, but also to our framework, so people can have a play around and figure it out as well. So I'm going to hand over to Alex, who's going to talk about in-memory fuzzing.
Hey. Cool, thank you. So James has talked about the BSD side, like fuzzing syscalls, but normally, like on macOS these days, basically a lot of the vulnerabilities are found in IOKit and the device driver stack. So my fuzzer focused on like IOKit and commonly found issues which in the device drivers. So that was things like IO connect call when you're passing data from user space to a device driver. IO registry, which is essentially like a persistent storage of properties within the database, which the device drivers will act on. Also shared memory mapping, so when a user space driver requests the kernel to map some memory, then the memory can be shared between user space and kernel space. Mesh messaging, which is the IPC subsystem, so one process to another process sending messages. And then finally, time of check and time of use issues. So to do this, I wanted to work on a combination of static analysis, static binary analysis, and yeah. Is that better? Is that working? Okay. Is that better? Yeah, cool. Thank you. Sorry. Yeah, so this will be a combination of static binary analysis, like how much data I can pull out from binaries, and also hook that up with dynamic analysis, how much information I can capture at runtime. I also want to do as much as I can in memory and without having to touch the disk. So this was developed in multiple different components. The first was a library which I called Coral Sun, which was used for, it's essentially a Python library to make writing code which interfaces from user space to kernel space easy and in Python. Then I wrote something called kxtlib, which is IDA-Python scripts for, you can run these on a device driver and pull out as much information as you can from the binary, doing binary analysis. And then finally, Opal Robot, which is the fuzzing harness. And well, it's a way of capturing stuff at runtime, but also doing mutation and monitoring and all the kind of common fuzzing, fuzzing like procedures. I'm using code names because I can't really name things, and it seems to be like the in thing currently. So there's similar approaches out there, like Tencent, Keen Team. They've got like similar fuzzers, or they've got like components, but they haven't really released any code. And I like believe in releasing as much code as I can to the industry to kind of so people can use it. So the library itself, the Cython library, it's a wrapper to wrap common IOKit C calls. So things like IO service open, when you're opening a connection to a device driver, when you're sending data between user space and kernel space using an IO connect call method. I essentially just wrote Python wrapper functions for the C because it simplifies, like it's really useful to have, say, I don't think you can see that. So using Cython, what would be maybe 20, 30 lines of C, you can simplify into like 2 lines of Python with like a wrapper implementation. And Cython automatically performs type conversions from Python to C without you having to write any kind of marshalling code and like type coercion code essentially between the things. So I thought Cython was quite cool because it allows you to essentially write unmanaged code, C code, inside of Python, which is a bit crazy, but also like perform like native memory management, like using malloc and things like that, while you're still kind of using Python syntax. So if that was like the Cython implementation, and then the Python side of that is like what would be maybe 50 lines of code is now like 10 lines of Python. So that's pretty cool. So I can just do things like opening a connection to Intel accelerated driver, sending some data using the IO connect call method, mapping memory between user space and kernel space, and like mutating the shared memory which is mapped between user space and kernel space, setting properties in the registry, just like a simple utility library. Okay, so now I've got my utility library. What else do I need to do? Well, basically the next stage was do some static binary analysis, find as much information as I could to pull out like statically from binaries. That was focusing on the kernel extensions, which are called KXTs. Basically, using IDA-Python scripts, it would parse the device drivers, the KXTs, extract that information, and basically build up a JSON representation of the attack surface. So that way, you can make tweaks to the attack surface, you can feed that into the fuzzer, and basically like consume that JSON and act on that. So I batch ran that against all of the kernel extensions. There's like hundreds of kernel extensions, which means the attack surface is quite large. Pulled out all of that in JSON format, and then stored that. So the sort of flow process is kxtlib. It's used for IDA creating the JSON, and then feeding it to my fuzzer called Opal Robot. So what do we want to pull out? Well, basically, we need all of the I/O services, which are the device drivers, the services which you can communicate from user space to kernel space. The I/O user clients, which are essentially the device drivers, attack surface. All of the dispatch tables. So when you call a method, it basically uses a dispatch table to locate the function in kernel space in the device driver on which to call. All the memory mapping and registry properties as well. So the sort of, I used two approaches for this. The first approach was using essentially using like code cross references and code flow analysis. So walking over, so when I was matching things like I/O services within the binaries, I would do things like loop through each function within the code segment of the binary. If it contains new user client and the name of the function, then I would find all cross references from that function. Then I would look up like type constants from the function and X references. And then if it fitted that kind of heuristic of my kind of matching algorithm, then I would add that to as a potential I/O service. I'd do the same with I/O external methods as well, which are these are like the function pointer tables and methods which can be called in each device driver. There's some downsides of this approach because it was kind of like rudimentary matching and not all. Like if you've got, say, indirect branches, then you can't like follow the code flow all the time, but it's only if like IDA can work out the X references automatically, but it kind of works. And then the second approach was just to do like dumb pattern matching, because when you so the I/O external method dispatch tables, when the compiler compiles the C code, it basically places these structs with their static values in the const segment of the binary. So you can essentially match on that if you know the pattern which you're looking to match. So say you loop through every line in the const segment. If there's a pointer, like a cross-reference to the code segment, followed by 4 32-bit integers, then it's highly likely that is an I/O external method dispatch struct. So that was a really good way of pulling out all of the structs. You could probably improve on this as well, like because it's all written in C++. If you understand like kind of like vtables and automating the reverse engineering of like the vtables, then you could do that. But my dumb pattern matching was enough to get the like fuzzing process underway. So, so what does this look like then? Essentially, you have so this is like an Intel accelerator driver converted to JSON, and then you would have all the user clients within the device driver. Then you would have all the selector numbers and like input and output sizes. So because if you're dumb fuzzing and you just throw like random input and output sizes, then the function's just going to reject your input straight away. But being able to feed it with like guidance on how big the data it expects as an input automatically is pretty useful. And it means that initial checks will pass. And then I would also do things like storing the memory segments within the JSON as well. So that was the static binary side. Then I wanted to, so some information you can't pull out statically because you don't have like samples of the data, so you're limited in like how deep you can go within the kernel side because it needs valid data. So secondly, I wanted to capture data at runtime, so I had sample data to basically use as my mutations. I wanted to make it easily extensible, so I wrote something in JavaScript to do this. And also know that I can definitely trigger the issues from user space as well. So I didn't want to do mutation in the kernel and then not be able to reproduce my bugs. Frida is really good. I'm quite a big fan of Frida hooking framework. It allows you to write JavaScript to hook functions. And the API is quite well documented, and it's supported for lots of platforms. So if you've not used that, I'd check it out. And then I essentially serialized all the data which I captured into pickles or JSON, and then fed that to the fuzzer. So that was implemented in 2 parts. There was a sniffing module, which would essentially do the hooking and capture of the data, and then the fuzzing module, which would load that data, mutate the data, check if it crashed, and then pass it to the and then test it. So here's an example of function hooking in Frida. You can just do like interceptor.attach, then the symbol name which you want to hook, and then you can write like on enter or on leave kind of methods and pull out all of the arguments passed to the function. It's really useful. Like if you've ever done like hooking in C code, it means you have to like recompile, re-inject. This just injects like a JavaScript interpreter in your process, and I use it quite a lot for mobile assessments as well. So there's some challenges. Like if you're familiar with macOS, then essentially the I/O service keys and mesh ports, they're kind of opaque handles. Like if you take one from one process, move it into another, it doesn't mean anything. So the solution was to basically just do more hooking, more capture, and then map these handles back to using a lookup table to the processes, so I could determine what had created them. So here's just a quick example of doing the handle mapping. With this function, I'm essentially hooking I/O service open, and I'm calling a native function inside of the JavaScript from JavaScript, and then finally logging out the arguments and capturing it. So after doing all the hooking, you end up with a lot of different pickled data structures, which essentially these are the device captures from user space to kernel space for each of the device drivers and each of the user clients with the selector numbers. And this is a good sample base to use for mutations in the fuzzer. Just that's what the sort of pickled representation looks like as well. So it's capturing all of the input arguments, the output arguments, the method numbers, and so on. And that can just be fed to the fuzzer for mutation. The problem with this is that when you run a process on Mac, it essentially does the same thing. Like it communicates with the Windows manager to set up the UI. It sets up kind of like default mesh ports and so on. It doesn't really do much. Like to actually get good captures, you have to be using the program for a while, or you need to be like navigating the UI menus and essentially generating that kind of data to capture. So what I did was I wrote some UI automation to basically just like drive the UI, like click buttons, click sliders, basically just simulate a user at the keyboard, so I didn't have to sit there and like drive the UI. So that was doing like loads of crazy stuff. So, but it was important to like blacklist like shutdown of calls, because my UI automation would like maybe shut down a VM and then I'd lose the captured data. So I'd be like, oh, that's not good. And then finally the mutation part. So I've got the static binary analysis output, the JSON. I've got the dynamic captured data. I basically feed that all into my fuzzer, choose the right data, mutate the data, make the call, and then use all the monitoring which we've created for the previous OSX fuzzer and crash detection and so on to determine crashes. That's the architecture for this. Like feed the JSONs in, feed the pickles in, do the mutation, scale it up across like multiple different VMs, and then finally pipe all my data into CouchDB. CouchDB is quite cool. I use that for a lot of my vulnerability research because I can run queries on lots of different crashes. to pull out interesting crashes and determine like exploitable crashes and so on. So just a comparison between the two kind of fuzzing approaches. I think this is a good indication that like different fuzzing approaches find different types of bugs, and yeah, and also kind of like certain fuzzes are good for finding certain types of bugs. Like OSX fuzz, it found a few like use after freeze, heap overflows, but generally the BSD side, BSD syscalls and mesh syscalls, like they're fairly well hardened these days. Like they've been around. It's like people have been fuzzing syscalls like since the 90s, so that's not really like, so it's reasonably mature code, apart from the new ones which are added, like which Apple add. Opal Robot, on the other hand, though, like IOKit, IOKit's always been a good source of bugs on Mesh, on OS X, but essentially, and it still is now. Like we're still finding quite a lot of bugs, like use after freeze, uninitialized memory calls, IO registry issues, out of bounds writes. I've got a number of issues which have been patched, which have got the CVE numbers down, but because triaging and like triaging's pretty slow, and reporting issues as well, like I've still got a number of issues which are outstanding to fix, but yeah. So in conclusion, I would say that the syscall fuzzer is good for finding use after freeze in the XNU code, like because of the approach of like creating objects, passing handles, then maybe freeing an object and then using it. It was kind of designed with that in mind. IOKit, still a really good source of bugs. The attack surface is huge. Like Apple are trying to add entitlements and so on to prevent like an app being able to actually communicate with the device drivers, or increasing the sandbox restrictions. But there's still quite a big amount of attack surface. Different approaches find different bugs. Like yeah, it's kind of obvious really. The need to focus on like it's good to focus on like green code, like new code. So if code is like has recently been added, then it's likely that it hasn't undergone as much like security assurance as old code. You can do things like I was like diffing the XNU kernel to previous versions to see what had been added, and then adding new fuzzing support around new areas of code which have just been added. Diffing the IOKit to determine what has changed in device driver stack, what new kernel drivers have been added, and then writing fuzzing for that. It's also like harder to scale macOS just because the infrastructure isn't really there. Like on Windows and Linux, it's quite easy. There's lots of code already out there, but Mac was kind of all from zero really. So the future work is more scaling. Like we want to yeah, just get more instances deployed. We were thinking about using like symbolic execution or constraint solving, one of the like more kind of like mathematical sort of academic type ways. But right now, like our basically like pattern matching and binary and like rudimentary binary analysis actually works quite well. So we didn't need to go as far as using something like Anger or Manticore. We'd like to move it to iOS as well. We'd like to have like a lot of different iPhones, essentially fuzzing or virtualized kind of infrastructure for that. Also more work on the IPC stack as well. There's lots of different processes which you can hit with mesh messages, which could be used as privilege escalation vectors. And then finally, further work on code coverage and feedback. Like we've got the code coverage part working, but actually acting on the feedback and like driving the fuzzer based on the output from code coverage is actually pretty hard. Because when we designed OS X fuzz, we weren't really thinking about code coverage. It was like an afterthought. Then it wasn't we didn't make some great design choices with that initially for code coverage. So lessons learned really from that. We've already released, this should be updated, but we've already released Coral Sun, which is the Python library for doing like quick IOKit calls. We've released OS X framework, but not all of the syscalls, because to be honest, like our syscall implementation is still finding bugs, and we don't want to like publish loads of stuff which will just like leave loads of ODAs in the world. So yeah. Then Yeah, and that's all on GitHub. And also, I'd just like to say thanks to all the previous research within this area. Like, I come from like a Windows background. I haven't really been doing macOS stuff for very long. But like Ian Beer from Project Zero, Mooney Lee, like Trend Micro, Fuzzing IO Kit, Keen Team, all those kind of people have been doing a lot of research previously in that area. So, cool. Are there any questions?
No? Okay, we'll try this.
Hi, so you mentioned that you want to look at iOS in the future.
Mm-hmm.
And I was wondering if you have taken the time to diff any iOS kernel caches with like XNU or OS X kernel or kernels. Just because the attack surface is smaller on iOS usually.
Yeah.
And sometimes slightly different depending on the version of iOS.
Yeah, definitely. So, yeah, it's a good question. So, yeah, iOS has got a much more restricted attack surface than macOS. No, we've basically just been working so far in getting our like more working on kernel debugging on iOS, like on the kind of the basics, the automation and things, but it's not really there yet. We haven't really investigated too much in in looking at like say kernel caches and that's probably the next stages. So yeah, thank you.
Well, and then one more side note. You were talking about just getting better fuzzing feedback for code coverage cases. And check out Laugh AFL. They have some pretty cool like means to get past things. But then also something that I've had success with code coverage is checking for instruction cache misses. So obviously, if L1 instruction cache miss, you're probably on a new patch of code. That's something that might be useful.
Yeah, definitely. So, I mean, things like SyszySan, which is Google's code coverage fuzzer, that's got, that kind of uses that. Our way is, so we've instrumented QEMU to essentially do that while using NCC's Triforce method. But yeah, we need to look into that more as well. Yeah, cool. Thank you.